Hi and welcome to this quick review clip on condensation polymers. Before we begin, you'll need to make sure you've got your independent study materials and notes, as always. And in addition, it's important to have a grasp of the meaning of these terms that I've put here in red. If you have flashcards on them, it might be a good idea to get the flashcards out. If you don't have flashcards on them, at some point it would be important to go away and to make a flashcard for each of them and make sure you've learned it as well. So I've drawn here two very simplistic representations of polymers to try and illustrate the idea of a repeating unit, or repeat unit. In the first one, you've only got one monomer. So the repeat unit will consist of just A. In the second one, further down, there's obviously two monomers, and the arrangement in which that they repeat themselves, AB, AB, would suggest that the repeat unit is AB. So this is something to watch out for when you're looking for a repeat unit. So this is a way you could draw out the formation of polypropylene, for example, which is an addition polymer, and the number of moles of monomer will equal the number of repeat units in this case. And this is signified by the use of the small letter N. So it's time for a little exercise to get your thinking moving. What you need to do is copy this out and indicate by labelling your diagram the repeat unit, the monomer, the trailing bonds, and the type of polymerisation. So hopefully that wasn't too hard just to get you started. So let's now move on to condensation polymerisation. At this point I'll be getting rid of the definitions at the top of the screen. So a polyester is a type of condensation polymer formed by ester linkages between the monomers. In most cases, water is removed and the reaction is the normal esterification that you looked at before. There's one exception, and that's a diacyl chloride plus a diol, where HCl is produced as the small molecule instead. So the third example is an interesting one, which we'll come to in a few minutes' time, but I'm about to ask you to have a think about these. So here's another exercise for you. Why not pause the clip and see if you can work out the structure of each polyester, but write it out as a repeat unit. So here's the structure for A. A couple of key points to point out before we go any further. Those points are the ester linkages shown in the middle, and the correct bonds are shown at each end. And also, trailing bonds should actually cross the square brackets. So it's quite a simple one for polyester B. So let's move on to polyester C. Now I must admit I've been a little bit mean. You don't get a polyester by reacting an acid anhydride and a diol. Let me try and explain. The anhydride doesn't have a reactive functional group at each end, but it'll still make a diester by reacting with a diol. The two ends of the diester come from when the acid anhydride splits into its two constituent carboxylic acid molecules. So what happens is these two carboxylic acid molecules, each one goes to a different end of the diol, as you can see on the diagram, to create two ester linkages. So we need to now go back and change our general formula for the reaction of an acid anhydride plus a diol. So why did I inflict this on you? Something like this could be expected within a larger polyesters question, maybe towards the end. Just when you think that the question is completely about polyesters, it wouldn't be beyond them to slip something like this in, just to see if you're actually thinking about what you're writing. Now it's not really being unfair, it is on the specification, it just requires you to think carefully about what's in front of you and not automatically assume that it's going to make a polyester. Just because something's a diester, more than one ester linkage, doesn't actually mean it's a polyester. It doesn't form a polymer, it forms a distinct molecule called a diester that has two ester linkages within it, but it's not a polymer. Okay, so let's have a look at the final one now, polyester D. So in the final one, again we've got the correct ester linkage and the correct trading bonds. But this time it was interesting to look at the mechanism by which this took place. It was esterification by nucleophilic addition elimination, a little bit different to the way that the other three would have reacted. Or should I say, a little bit different to the first two. The acetal anhydride would definitely have been nucleophilic addition elimination as well. So let's have a look at which part of the repeat unit came from where. So using the colour coding, hopefully you can see the part of the polymer, the repeat unit I should say, that comes from the diacyl chloride, the ester linkage in the middle, and then finally on the right hand side the part that came from the diol. So now let's look at a couple of examples. So this one shows 2-hydroxypropanoic acid, which is commonly known as lactic acid, esterifying with itself to make PLA or polylactic acid. So polylactic acid has a modern application in biodegradable 3D printing. So why mention biodegradability? It's because ester linkages contain polar bonds, which are therefore susceptible to hydrolysis in acidic or alkaline soil. So hydrolysis is the breakdown of a molecule into smaller molecules due to reaction with either water or hydroxide ions. So we can apply this to a specific polyester. This particular polyester is called terylene, and it's used in tents, bike covers, and there's also some marine applications such as sail construction that it's used in. So it's a very strong polyester that we can make strong water-resistant cloths out of. And there's its systematic name, just in case you wanted to know what that is. It's still susceptible to hydrolysis though. So let's have a look at the equations for these hydrolysis reactions. Now, although they're both hydrolysis reactions, it's very important to make sure that you know the two different sets of products and be able to think about them, remember them, and apply them to previously unseen polyesters in exam questions. This is a very popular style of testing your knowledge in A-level exams. So let's now have a look at polyamides. So polyamides are also easily hydrolyzed due to polar bonds in the amide linkage. So the amide linkage arises from the reaction between a carboxylic acid and an amine. It's written in structural form as CONH and is located between the two monomers in the repeat unit. So you can refer to the equation on the screen to show you what happens to the amide link when it's hydrolyzed. So the dipeptide isn't actually a polyamide. So dipeptides and polypeptides are formed in the reaction of amino acids with each other. So don't forget you've got a carboxylic acid end and you've got an amine end. And one is acidic and the other is basic. So obviously they're going to react with each other. And if you were to hydrolyze a dipeptide, you'd break the bond between the carbon and the nitrogen in the amide linkage, or peptide linkage as it's called here. So although I've just said that they're essentially the same thing, there's a slight difference between the two terms. Although I said they were the same atoms, if you look a little bit wider in the molecule and you see that your CONH linkage is between two amino acids, then it's called a peptide linkage. It can still be referred to as an amide linkage, but peptide linkage, I would say, is a subset of the amide linkage idea. And A-level biology students will be familiar with the idea of a peptide linkage because it's found in biochemistry such as DNA and proteins. So this shows the formation of the amide link in Kevlar by the reaction of two aromatic monomers. So this polymer is very, very strong, and it's used in bulletproof vests and the neck braces that Formula One drivers wear to protect them in high-speed crashes. And this very, very important polymer was discovered by Stephanie Kwolek, who was a research chemist working for the DuPont chemical company in the United States. And in 1965 she came up with the structure and was able to synthesize it and prove how strong it was. And it's saved countless lives since in protective gear, and has had many, many other applications in engineering and structural engineering situations where strength is needed. So here's a classic way to make a polyamide. A little question for you. Instead of a carboxylic acid, suggest another monomer that could be used, and have a think about why this isn't actually done in industry on a large scale. So pause the clip, have a think about it, and then come back when you reckon you've got an answer. So hopefully if you remember your carbonyl derivatives, you'll have a think about diacyl chloride perhaps, because we mentioned it earlier. But the problem with diacyl chlorides is the small molecule is HCl, which is toxic and has to be dealt with. And the reaction itself is actually pretty exothermic. It's very reactive too, so it's quite difficult to control. So let's have a look at making nylon, or nylon 6,6 as it's called in the industry. So to start things off, I'd like you to try and draw the skeletal formulae of the two monomers. Obviously pause the clip. So hopefully you got these two structures as your skeletal formulae. So pause the clip again and have a think about how this might work. You need to remove the water from between the COOH group and the NH2 group and write out a repeat unit. So the way I do it is to write out the amide link first of all. That allows me to visualize what comes off on either side, such as these two. Now I can replace them with the carboxylic acid and the amine that we're dealing with. So we get our repeat unit looking something like this. So we have our amide linkage, the section of our repeat unit from the amine, and finally in red the section from the carboxylic acid. So that brings us to the end of our review of condensation polymerisation. Hopefully it's been fairly useful and it's taken you through some of the different types of condensation polymers that we have, how we make them, how we hydrolyse them. But now is a good idea to go and practice some examples, particularly making sure that you're getting the trailing bonds and the repeating units done correctly, because that's where most people seem to struggle. Okay, so until next time, thanks for listening and see you soon.